My name's Jeffrey Russum, but my colleagues at Indeed know me by another name, Bongo, so you can call me Bongo. But I'm here today to talk to you about how Indeed has built its new Agentic Talent Scout hiring, AI hiring solution using federated subscriptions. So say you're in the position like Indeed was, where you were tasked by the CEO to build an AI chat solution very similar to chatgpt.com. And here you see we have like an example where you type into chatgpt.com and not only does it respond to you, but it streams it back to you in near real time. And as an engineer, if we were to think, well, how would I build such a streaming solution? The immediate streaming technologies that would come to mind would be things like server-sent events, i.e. SSE, or WebSockets. And sure, that works fine for plain text and markdown streaming responses, but what if you need more than that? What if you want to build rich experiences that require rich structured data, say from your supergraph? Well, I'm here to tell you that subscriptions, and in particular federated subscriptions, allow you to do just that. Stream rich structured data from your existing supergraph deployments. And let me show you how we pulled that off at Indeed. Let's see. Whoop, whoop. There we go. Okay, so this is Talent Scout. This is Indeed's new AI hiring assistant for recruiters. And it's capable of doing many different things, such as returning job performance metrics for a specific job post on Indeed. And you'll see here it brings up various different metrics like impressions, clicks, application starts, sponsored versus organic traffic to inform your budgeting decisions for sponsorship, weekly trends. And based on that data, you can ask follow-up questions like how to improve my job post on Indeed, and it will suggest things like a salary range, using data from Indeed to suggest an appropriate salary range based on the market that job post is in. Ooh, okay. And so that was Talent Scout. And for the rest of this talk, I'm going to go through first why subscriptions and why it made sense to use it for Talent Scout. Then I'm going to talk about how we built Talent Scout using Apollo and Federation. And third, I'm going to talk about what federated subscriptions unlocks for us. So what was the challenge we faced? Why did subscriptions make sense for our use case? And as I hinted at the beginning of the talk, one of our first thoughts was to use something like SSE, server-sent events. And we thought about it for purely pragmatic reasons. We already had an SSE system at Indeed that was built to power the bell icon notifications on the employer site. So we had like a bell icon, and it would light up and show all your notifications for important things happening on your account. But since that system was never built for a real-time chat application, it had several major cons. First, that system did not support streaming any sensitive information, so PII or information that requires authorization checks like candidate details. Like you want to make sure that the user that is viewing that data streamed up has access to that particular candidate. And in addition to that, since it's a text-based streaming protocol, there's no type safety. You're just getting strings. So it was all up to clients integrating with this SSE endpoint to handle validation in the client to ensure that the data was valid coming up. And as a result, it was not a great experience for developers. But we had a time crunch, so we tried to make do with SSE, and we built a prototype. And this is at a very loose, high level what that prototype looked like. And it consisted of three major architectural components: the Scout UI, which is the front end, the Scout backend, and then the SSE pipeline to send notifications from the backend to the UI. And essentially the way it worked was when the user types a message, the UI would post the message to the Scout backend. The Scout backend would process that message asynchronously. And once all the agents, participating agents in that conversation had finished responding, since this is a multi-agent application, the backend would send a notification, an SSE notification up to the client to tell it, hey, all the agents have finished responding. Please refresh the conversation history, at which point the UI would make a regular GraphQL call to refetch the conversation history to get all the messages, including the new ones that had been added. As you can probably tell, there's a couple of problems with this architecture. First off, it's highly inefficient. We're essentially making 3 network hops, one for the SSE, and then a full round trip to fetch the updated conversation history. And for us, the more pressing problem was what to do about multi-agent experiences. Since we were only able to send a notification when all the agents were done processing, that meant that if 2 agents needed to respond in serial, say the job performance agent responding with a job performance card, and then the next best action agent suggesting a follow-up prompt for the user to select from, the system would have to wait for both of those agents to finish responding before it could send the notification, and thus delaying when we can show the job performance card. And so we stood back and think, well, we have various different options to address this problem. We can make the querying faster. We could try and send more SSE notifications. But we stood back and thought, hey, Indeed is all in on GraphQL and Apollo. We use GraphQL for virtually everything. The SSE pipeline was the only thing that was not GraphQL in this UI. And so we thought, let's try subscriptions. We haven't done it before at Indeed, but this is literally screaming to use subscriptions, so let's try it. And we did a little bit of research, and we looked into our Apollo router installation, and we saw that it was just very minimal configuration to get subscriptions up and running. It's literally just some YAML config. In hindsight, I kind of wish that I had a screenshot of it here, because it's literally just a couple lines of config. But that's how simple it was. Second, the GraphQL framework that we use, Netflix DGS, already supports subscriptions and had supported it for years. And so we thought, let's try subscriptions. Let's try streaming up the messages as they become available from each agent. And this should fix, in theory, our multi-agent problems. So with subscriptions, theoretically, we should be able to post a message from the user to the backend, process it asynchronously, and as each agent in Talent Scout responds, it should be able to stream each of those messages up. And we can leverage our supergraph and all the existing authorization checks that are already built in our graph for all our non-streaming use cases. We should be able to safely stream up whatever we want to the client. And so subscriptions make sense for streaming, but as you all are probably aware, streaming isn't the whole thing. That's not your whole architecture. And there's a lot more to building a chat than just the streaming pipeline. So let's look first at the requirements we had when thinking about how to build Talent Scout end-to-end with the chat pane and everything. We had 3 key requirements at the time. First was the Talent Scout had to be embeddable. It had to run not only on Indeed.com, but it had to run on our partner ATS websites, such as iSolved and Workable. And in addition, it also had to run in the Indeed Chrome extension for use in other ATS partners that didn't use our SDK. Second off, reliability was critical. We knew in most cases we only had one chance to make a good first impression with a recruiter using our chat app. Anyone who's ever tried a chat app before, if you go in and type something and if it doesn't work, if it blows up in your face, you're very unlikely to try it again. So we wanted our streaming infrastructure to be rock solid. And third, we had a fairly aggressive timeline. We had 9 months to go from absolutely nothing. And when I mean absolutely nothing, I mean the engineering team and product team had no experience with AI, to having something built, tested, deployed, ready in production by Indeed's September FeatureWorks conference. And if you're looking at your calendars, you can see that that was exactly a month ago. So we've been in production for about a month. So with those requirements, this is essentially the architecture that we arrived upon. On the UI side, we have 2 major pieces. the runtime UI SDK. This is an SDK that is capable of deploying an Indeed React application on any website, whether it's Indeed.com, an ATS partner website, or Indeed's Chrome extension. This was built thanks to the Shadow DOM. Second, this dropship SDK hosts the actual UI implementation for Talent Scout. This UI application is a fairly standard GraphQL first React application built on top of the Apollo client. This UI layer then talks to Indeed's federated GraphQL gateway, known as OneGraph, which is powered by Apollo router. And sitting at the center of the GraphQL API for Talent Scout is the Scout Agents API, which is our subgraph that supplies the conversation mutations, queries, types, and subscription for Talent Scout for the actual conversation API. This GraphQL subgraph then integrates with the Scout Agentic core, the Scout Agents core in the diagram. This is the actual agent implementation built on top of LangGraph. And this subgraph and the Scout Agents core interact with each other using either an internal REST API or via the Redis pub sub channel for asynchronous communication. And in addition to those Scout core major components, Scout itself also relies on a fleet of feature subgraphs pre-existing in the Indeed supergraph. I think last time I counted it was something like 40 separate subgraphs that the experience as a whole leverages to power the entire experience, in addition to just the conversation subgraph. So now let's zoom in on the talent subgraph in particular that powers the conversation experience. First off, when you think about subgraph for a chat experience, such a subgraph as you might expect defines a conversation API. This is to allow a chat UI to do typical chat-like things like creating a conversation, posting a message to a conversation, and supplying some set of queries for fetching conversational history. If this was just a simple text-based messaging app, this is probably all I would have to say, but what about rich data? We knew from the start that plain text or markdown wouldn't cut it, so we needed a way to supply rich data in addition to text. So to support rich data, we adopted a message schema like the one you see here. And the approach we took essentially allowed one of three separate ways that an agent integrated in the Scout could supply rich data to the UI. The first way an agent could supply rich data is to simply use vanilla federation. This would involve federating the entity of choice, say the sourcing profile, onto the Scout message data field, in which case, for an agent to return, say, a list of these entities, all it would have to do is return a list of the key field identifiers, at which point GraphQL and Apollo router and the UI take care of the rest in terms of hydrating any data that the UI needs for that particular entity. As an example here, I have the sourcing profile. This is a pretty standard entity at Indeed that essentially represents a job seeker account on Indeed, including information about the job seeker as well as any attached resumes. And so if you had an agent that wanted to return, say, a list of resumes, suggested resumes to go along with a job, all the agent would have to do is return a list of key fields, in this case ID fields, at which point the GraphQL infrastructure, Apollo router and UI are able to hydrate anything the UI needs. The backend agent is completely oblivious to what the UI is actually rendering. However, sometimes we don't always have a single entity ready, or there might be more than one entity that's applicable for a particular use case, or there might be complicated query paths to get the one or more entities that you need. A really good practical example of this in Talent Scout is if you wanted to ask Talent Scout for a list of candidates who have applied for your job, so sent in an application. Unfortunately, asking such a question at Indeed is a little complicated because an applicant at Indeed could refer to an applicant in our legacy candidate management system that powers our SMB experience, or it could refer to a candidate application that came in from an external ATS partner via our inbound candidate sync API. And in the existing supergraph, if you wanted to just use the existing supergraph, the UI would have to call both of these entity types, stitch them together, and figure out how to dedupe and solve a complex problem. So instead, agent implementers had the option to implement a Scout-specific type, in this case, a Scout application that would hide all this accidental complexity from the UI and experience layer. Those of you that are familiar with domain-driven design might immediately recognize this as the anti-corruption layer pattern to shield an experience from any legacy accidental complexity. So in short, so far, an agent can return either an entity ID for an existing entity in the supergraph, or if no such entity exists, the agent implementer could create an anti-corruption layer type within the subgraph. But what about data from agent tool calculation, so like actual number crunching? The job performance score that I showed in the demo is actually a pretty good example there. We're returning like number of applies, candidates, numbers. Those are things that don't necessarily correspond to a queryable entity in the UI. So for this particular use case where an agent just needed to crunch some numbers and return numbers to the UI, we created an escape hatch for an arbitrary JSON content field in the schema on the Scout message data type. And a lot of you might look at the schema and immediately scream like, hey, this is GraphQL. Shouldn't we be typing everything? Like, why are you throwing type safety to the wind? In a lot of cases, like I empathize. Like if I was initially reviewing this schema, I might say like, what is this JSON thing doing here? Like, why have you done this? However, in our particular case, we wanted to be able to try out many different agent implementations and experiment quickly with the types of agents and tool calls and data that we would supply. And so we opted for an approach where in those cases where there was an existing entity, an agent implementer could create a content type of their own and specify the type of that content using the message type field. And then all the agent would have to do is define that message type definition in the backend agent implementation, and then supply a UI implementation, and then reuse the existing schema in the Scout Agents API without having to touch the Scout Agents API schema. This allowed backend teams to experiment quickly with creating a new implementation, a backend agent implementation, and a new UI surface area so that we could experiment very quickly and arrive on a good fleet of agents for our initial experience. So that covers the chat message type itself and how we send rich data on the chat messages themselves. Let's now look at the subscription type itself. Since users will only ever be conversing with a single conversation at a time, we opted for a subscription type that is scoped to an individual conversation ID. And we started with 3 event types. A progress update event type so that an agent can inform the UI of what an agent is working on. This can be things like uploading, parsing a file, or actually crunching some numbers. Then there's the Scout message available type. This is the actual magic sauce that streams up the whole Scout chat message to the client. And then finally, there's a Scout response end event type. This is an event type that signifies to the UI that all participating agents in the conversation have finished processing the user's request and that the UI is now free to allow the user to start the next turn of the conversation. And what I like about this schema is that it's very extensible. Like, for instance, you'll notice that in our initial implementation, we don't support token streaming. But with a schema like this, we can very easily add on token streaming by adding a new token event type to the schema. And this is something that we actually plan to implement in Talent Scout soon in the coming months. This is where GraphQL shines. You can strongly type each new event type, whether it's message available, token delta, or document line edit. That's like a teaser for a little bit later. And you're able to stream up whatever you want to the client. So That's it for the schema. Let's now talk about how streaming is actually implemented. So when talking about like how subscriptions works at runtime, I like to think of it as a 3-stage life cycle of a subscription phase where you're subscribing to a topic. There's the posting a message phase, and then there's the receiving the response phase from the back end. In the first initial phase, the UI opens up a long-lived HTTP connection using a streaming-friendly protocol. Think multi-part mixed or chunk transfer. This protocol is not only browser-friendly, but it's HTTP intermediary-friendly. Apollo Router, in turn, then sets up a WebSocket connection to the underlying Scout Agents API subgraph that implements the actual subscription resolver. Then upon initialization of the WebSocket connection in the subscription resolver, the Talent Scout subgraph subscribes to a Redis PubSub channel that is specific to that conversation. Then, once the subscription phase is done, we now enter the posting phase, where a user types in a message in the Scout UI, and when they click send, the UI posts the message using a GraphQL mutation to OneGraph, which then passes everything synchronously down to Scout Agents Core. Then in Scout Agents Core, once it receives the message, it in-queues the message into an internal queue for asynchronous processing, at which point we then enter the receiving phase. During this phase, the in-queued message is popped off the queue and picked up by a background worker, and it's processed through the Talent Scout LangGraph implementation. And as LangGraph processes the message, any messages that any agent in the LangGraph graph emits and is intended to display for the user is published to the Redis PubSub channel for that specific conversation. At this point, the subscription resolver picks up the agent message reply and streams it to the Apollo router. At this point, this is where a lot of the magic of federated subscriptions happens. If that message references any federated entity, such as sourcing profile or applications or anything like that, Apollo router will then make out federated queries to fetch the data for that federated entity over regular HTTP. This is like honestly the magic of federated subscriptions, because in this flow, the sourcing profile subgraph or any other existing subgraph is completely oblivious to the fact that its data is being fetched for the purposes of streaming. This means that any authorization checks or capabilities that you have built in to an existing subgraph that expects HTTP will continue to work, since the Apollo router instance can be configured to send any session information automatically and basically fake to the router that this is a traditional boring HTTP connection. Then, after all those federated queries are completed and Apollo router zips up all the data into the final subscription event, that event is shuttled over the persistent HTTP subscription connection to the final UI for display in the UI. So after we implemented all this and built it and deployed it to production, we had some fairly immediate results. First off, the overall P95 total response times for receiving messages decreased by about 22%. Secondly, and more important for the experience overall, for those multi-agent workflows where more than one agent needed to respond in serial, that first initial message, so like the job performance message as an example, is able to be delivered on average about 2 seconds faster than it was with the previous SSE-based architecture. And thirdly, important for like maintenance and upkeep, we had one less service dependency to worry about. We were able to consolidate 100% on Apollo router, and we no longer had to rely on our SSE infrastructure. But there's broader potential than just plain old faster performance and faster response times. Once you have an extensible streaming solution in place, you can start experimenting with other streaming event types to bring to your experience beyond simple message sending. For example, collaborative document editing between a user and an agent. This is a picture of a prototype we actually have at Indeed right now. We're experimenting with collaborative editing. So in this particular mode, you could have essentially two streams that an agent or user could interact with. The one being the conversation page for traditional message passing, and another stream for document inline edits in, say, like a document, and say like a markdown document, like in here we have a markdown document of a candidate shortlist. And as with all large projects like this, we have a couple of lessons that we learned from all of this. First off, an important lesson is, even though streaming's super great, not all customer networks allow streaming protocols like SSC and WebSockets. This is especially true of corporate environments. So in the case of Indeed for employers, we're dealing with customers who are recruiters that are in a corporate environment. It's very common to have very strict security settings, firewall settings, VPNs that effectively disable any streaming technology whatsoever. So if you're targeting such customers, it's absolutely critical to have a graceful fallback in your experience, something like, say, polling or a synchronous API. In the case of Talent Scout, the experience actually detects whether or not a subscription will succeed or not, and if that attempt fails, we fall back to a polling experience that, even though it's slower, it still works, and those particular users are still able to use Talent Scout. The second lesson that we learned, and a recommendation that we've developed as a result, is that when you build out a subscription resolver, in particular, if you want to use WebSockets, many frameworks like Netflix DGS can introduce some accidental complexity, because a lot of these framework implementers kind of assume that HTTP is the transport protocol, and WebSocket support can be treated almost as an afterthought. This means that sometimes your resolver implementation might need to be aware of the differences of HTTP versus WebSocket protocols. The very concrete example in our case is passing session headers forwarded from the client experience to load up the session for the user. If that header is forwarded through to the experience, for a WebSocket connection, there is no header. So that session information has to be passed through different means. And so your resolver might need to be aware of this. Because of this, we actually recommend leaning even harder into federated subscriptions and having a subgraph that is dedicated only to the subscription resolvers, which means that only the subscription resolver has to be aware of HTTP versus WebSocket, and all other subgraphs doing data hydration can just rely on the Apollo router to make those HTTP federated queries, which drastically simplifies the implementations of your entity and query resolvers. So some key takeaways here. We showed how subscriptions can be much more powerful than SSE and WebSockets. In particular, I like to think of subscriptions as a rich data streaming platform. When you have something like, when you have a supergraph in GraphQL, you essentially have a rich data catalog, and federated subscriptions enables you to stream that rich data directly to your clients. Thirdly, Apollo router includes nearly turnkey support. In our experience, it was just literally 5 lines of config. I kind of wish that I included a screenshot. I didn't include it because of just how boring it was, but trust me, that's literally all we had to do to configure subscriptions to work on Apollo router. And with Apollo router, you're able to stream data from your existing supergraph implementations with virtually no changes. So I go out and I challenge every one of you to build your own rich AI streaming experiences using Apollo router. And as a closing thought, I say that subscriptions are the future for rich streaming in GraphQL first applications, and I invite everyone to join us. Thank you. All right, questions?
Hi, thank you. So now I realize that this was built like incepted 9 months ago. A lot of stuff has changed
Yes.
in the AI streaming world, and now we have the Vercel AI SDK. So I was curious if you had to build the same experience today, if you would still lean on subscriptions, or maybe you would investigate something like the AI SDK to build something like this.
Yeah, I mean, obviously, like, since we started this 9 months ago, like, at the time, things like MCP were still, like, extremely new. It's hard to believe. And we definitely are having internal talks right now of, like, what are things that we could do differently. Like, I know some of the things that we're a little excited about is things like MCP UI. And particularly, we're excited about those because for experiences like Talent Scout, we want more control over the rendered UI experience and the rich content, and things like MCP UI make more sense for us. But yeah, definitely, if we were starting from the beginning, we would probably lean more heavily into some of those tools. I still think that we probably would have used subscriptions even in our case, just because it's so much easier to. You have essentially a near out-of-the-box streaming solution already in place, and that was the big thing for us. Like, we essentially, the only streaming solution we had set up and ready to go was SSE, and it literally only let us send up essentially enums and IDs. And if we wanted to build something else, we would have had to build out that pipeline. And for us, it just made sense, especially if we're talking about reducing costs and need for multiple API teams. It just made sense to. We had an API platform team for OneGraph, and we just consolidated all onto that. And so it greatly simplifies a lot of things, maintenance-wise and platform-wise.
Okay, thank you.
Yep.
Hello.
Hi.
Firstly, thanks a lot for the talk. It was very good. We're actually building something very, very similar, so it's almost exactly the same.
Nice.
So it's nice to have that validation. We're a few months away from prod, and you've been in prod for a month now.
Yeah.
What are the biggest things that have gone wrong? Not necessarily just related to subscriptions, but your multi-agent orchestration. What's gone wrong, and what would you caution someone like me with?
What I've always found funny about this project in particular is when we first started through it, there was two things that everyone thought would break. Everyone thought that the AI, the LLMs would hallucinate like crazy. That turned out to be true. And so we spent a tremendous amount of time with data scientists and evals to get our prompts to a point where they didn't do random things or invent job data. So champing down on hallucinations. And it's hard to tell how much of that was us like improving our prompts versus like the LLMs just getting better, because the LLMs were getting better. And the other fear we had was that subscriptions would blow up in our face and would be a bottleneck. And when we tried to load test the system, subscriptions was never the one that went under stress. It was always something else. It was always running into like OpenAI issues, or running into like the Python backend Flask application, like not being able to scale up with more traffic. And so I confidently tell people that like subscriptions has never been our bottleneck and probably won't for our particular use case. But if you're talking about like thousands and thousands of concurrent users, like, might be the case. But yeah, it's about what you would expect. AI LLMs doing LLM things has probably been our biggest challenge.
Okay, thank you.
Thank you for the talk.
Yep.
So my question is that you are using HTTP multipart for the streaming. So there is some polling interval involved, and that polling interval governs how much Apollo would actually charge for the subscriptions. So how did you go about that? And then you mentioned somewhere that enterprise applications, enterprise environments, they have strict firewall policies
Yeah.
which prevent subscriptions from working.
Yeah.
But since you are using HTTP multipart, why did you need a fallback is the second question.
Yeah, so I mean, disclaimer: I'm not a network expert, but what we did run into what we did run into was security software that would want to buffer the response, and essentially, since these are long-lived connections that never end, they would just get cut off. And one of the hints actually where we discovered where this might be an issue was actually our own Indeed security experts, like trying to run security audits on our tool, and then our Talent Scout wasn't working. And we sat down with some customers trying to use trying to run Talent Scout in their environment, and unfortunately, that customer wasn't able to. We weren't able to get a hold of their IT department, but at least when we observed their network traffic, we noticed that both SSE and the long-lived HTTP connections for multipart didn't work. So that data informed us that there are plenty of network configurations that disable the multipart mixed streaming, and which led us to create a fallback. And so far for our beta users, it's about 3% of users that run into this issue. So it's not overwhelming, but in our case, since it's like corporate networks, that meant that 3% might be an entire customer account couldn't use Talent Scout. And so that's why it was very critical for us to implement a fallback.
Okay, thank you.